Easy.
I slept in that for 4 days. Yeah. I can pass out. I have no.
Someone.
All right. How about we get started?
Enough that I think I could read a paper.
So good morning. My name is Leonardo. I am a postdoc here at QuantumSavory. I work with Stefan as well as Don and Diana in the quantum information science group. And today I have the challenging task of finishing you off for good for this summer school. Hopefully you're already far along the way. I am. So, well, we're going to talk about simulations today. So I will do an introductory blurb. I'll try to make it understandable for both CS community and physics community backgrounds because it has value for both these communities. Well, let's start from the physics blurb. Usually when we think about simulation, we think about emulating a real system in usually a computer, a machine, something that's not the actual system, right? And this is true in general. The kind of simulation we're going to talk about today is the distributed systems simulation. So simulating systems that are composed of multiple elements that interact with each other over time. And for people with a quantum information science background, this might recall what you would think in terms of LOCC. Local operations, classical communications is a framework in which there's multiple components in a system that communicate via classical messaging, and they can apply local operations / measurements on their local quantum systems. So there is no distributed quantum operation allowed without, except for agreeing using classical messaging. And this is the paradigm that we usually assume when we do entanglement distribution, which is going to be the topic of the afternoon session. We're going to instantiate everything we learned today, specifically for quantum network simulation. But what we learned today is in general more applicable to all systems that behave this way. We have multiple components. They communicate and synchronize using classical tools, such as messaging or using shared resources. And locally, they can apply all sorts of computations they want. So this is what we're going to work with today. And it's hard to model these systems using an analytical formulation, because usually when you want to simulate an actual system, you're going to incorporate delays, you're going to incorporate imperfections, you're going to incorporate losses, which are hard to incorporate in an analytical system. So usually what ends up happening is that you are going to model your system in an analytical fashion or in another way. And in doing so, you're going to have to idealize some properties of the system. So you get, for example, a transfer function. If you're in robotics, you are going to get a Hamiltonian / describe the system as an open system dynamics and so on and so forth. Or if we're talking about networks for CS people, you're going to model the network architecture as a fluid model. All these terms don't have to make any sense to you. It's just different analytical models for different kind of systems. But then you solve those and you want, okay, but if I want to deploy this solution in real life, does it make any sense once we deal with real life constraints? And that's when simulation comes into play, because it's cheap. You don't have to deploy anything, and it's a fast check to validate if the solution you have is robust to real life dynamics and imperfections. Okay, so I'm done with my initial blurb. So if we want to, so the main thing that's going to be with us for this whole 3 hours is the concept of time evolution. So time is going to be the key, because we need to track time over the course of our simulation. And to do that, we need some sort of server. So we're going to have the core engine that allows our simulation to evolve and to be consistent is a time tracker. So this is the time tracker it's going to be present in every simulation system. Right. So if I didn't know anything about simulation, and I imagine, yeah, I have this very complicated system I want to simulate, how would I do that? So the first idea that usually people come up with, and when they implement their own simulations, I see a lot of people doing this, which is fine for a lot of situations, is the following. So imagine this is your time line. It goes from 0 to some time t. And you discretize it in several time steps. And every time step is delta t long. And then what you do, you have that time tracker server basically evaluates the state of the system at the end of every time step, computes how the system will evolve for the next time step, and then updates the state of the system. So this is a very standard practice. And it works, and it's in fact how, for example, hardware is usually described. So hardware logic is done according to this fashion because hardware itself evolves using a clock, right? So that's how you do it. But can anyone guess what is the problem in doing this for simulation of distributed systems? Why is this not the best approach?
You can't parallelize it. You're always waiting for the last time.
That's something, but it's also hard to parallelize what we're going to see at the actual solution after. So that's a problem that's in general.
This would, oh, sorry.
No, go.
With distributed systems, you're kind of assuming that the clocks of those systems are perfectly in sync, and maybe they're not.
Yes, so that to me that translates into you're approximating things. So you have to evaluate something at the end of every time clock. You're assuming that things have to evolve at the same time. It's not exactly how the system will actually evolve in real life. So that's one thing. I saw more hands up. Oh, sure.
If you time bin, then you're gonna struggle, like if there's multiple events maybe happening in.
Right. So all events that happen not at the same time but within the same bin, are going to be processed together. So again, it's not exactly ideal. So this is one of the two major drawbacks. The second major drawback is that imagine the system you're simulating is something that it's a system where on average something happens every 10 seconds because that's how the system works. But your time step is 1 nanosecond. So you're going to spend 99.999% of your time to process time steps in which nothing happens. So you're going to spend basically all of your time doing nothing. And so the main problem here is to have to tune exactly the time step so that it makes sense for the dynamics of your system. In doing so, you're still going to have some approximation degree in your simulations. So there is a way to get around this and have something that works without an up-to-machine, floating point precision. We can get rid of this approximation. We can have the system itself decide the time scale at which updates of the state will happen. That is based on how the actual system that you're simulating works. And this is called discrete event simulation, which is what we're going to talk about today. So the idea is that we go back to our timeline, which is going to stay because we do need to simulate time. So first of all, just to see who has worked with discrete event simulation earlier in this group. Okay, couple. Okay, good. So we have our timeline. The way we're going to do it is we have a server that is going to be our time tracker. And you can imagine the things that happens in the simulations are called events. So let's imagine what we're simulating is you sending a request to a web server, say GitHub, to download a repository. Okay, so at time, so the user at the beginning starts the simulation by creating an event. So it asks the server, I want to create an event at time t1, and I created an ID for the event, and it's going to be, we call it HTTP, because it represents your web request. So the server, what it does, the server is the only one that has control over the timeline. So the server receives your event request, the server internally holds a queue of events. Okay. The server schedules your event within the queue, and the server will be in charge of scheduling your event at time t1. All right. At the same time, but what happens when I schedule the event? The way you design discrete-event simulation is by defining a callback function. So you're going to have a function callback that you associate with the event. And this function, you specify that it should be called when the event fires. So you basically, the way you design the simulation is by designing when events arrive in the system. You let the server schedule them. And then you define how the system should react to events when they fire by using callback functions. If for any of you who are familiar with usual programming with of computer systems programming, this should be pretty similar to the external interrupts paradigm in programming. You don't have to know this, but if you do, it's a plus for you. And the server will manage concurrency, will manage event. So say there's a bunch of events in the system, T1 and T2. Say at T3, there's 2 events scheduled. The server will manage all of this for you. If any event comes, say these events are scheduled at this point in time. So the actual simulated time state is still here. So we are still here. But in the future, there's already a bunch of events scheduled in the future. So that as of now, if anything more happens after the callback for this last event happens, the server will just evolve time up until T1 and fire the next event, right? But if by calling the callback function for this last event that's been simulated, but if by calling this function callback creates a new event that will happen before T1, say at T0 here, then after the callback, the server, what will do, it will, instead of scheduling T1, it will evolve time up to T0, not T1. So that's how the server manages events. And this solves the time step problem, right? Because if the next event in line is 10 seconds from now, you're just going to evolve the system by 10 seconds just in one shot without having to do all the time steps thing. Honestly, this is all the theory behind discrete-event simulations. This is all it is. So it's pretty simple. One word about how does the server do this. If you're smart about the data structure you used inside to hold the events, then it's computationally pretty simple to do this. And usually you can look them up. The 2 data structures that make sense are the heap and the calendar queue. You can look them up how they're doing. But the gist is that taking the minimum from those data structures is very cheap. So that's why the most common operation, because you want to schedule the event that's closest to you in time. So the extracting the minimum from the data structure is your key operation here. All right. So now we're going to. This is the theory. Yeah.
Sorry. This might be a question that should have come up 5 minutes ago.
Okay.
But can you give me an example of the kind of evolution or the kind of Hamiltonian that you're trying to simulate here, and what an example of an event is?
Right. So for now, don't think about Hamiltonians. For now, there is no quantum. We'll come to quantum later. For now, think about the fact that you're trying to simulate a system with many parties that are communicating with each other over time and synchronizing with each other. So say, for example, you are at the supermarket. I want to simulate how the queue of the supermarket works. And for example, the queue works, I'll go there. You're at the supermarket, for example, you're at Trader Joe's. So you have a queue of people in line. Wait, this is not actually Trader Joe's. So you imagine you had a single queue of people and then many cashiers, many tills. And the first person in line, as soon as one of the cashiers frees up, can can walk there. And this will take some time. And maybe if I walk to the closer one, it's going to take less time than going to the further one. So you have to model people arriving in the queue over time, and each one of these will be an event. You have to model waiting time while you're being served at the cache, by the cashier. And you have to model the time it takes for you to, so say there's the event that the guy that was being served here is done and leaves. So this is an event. The event fires. The callback will be, the callback function, it will look like as follows. The callback function looks at the top of the queue. Oh, there is a guy here waiting. So, okay, let's schedule a new event from t plus delta t, where delta t is the time it takes for this guy to walk here. At t plus delta t, we start serving this guy here at this cache, by this cashier. And then we move on. That's how I would model this kind of system in a discrete event simulation. So this is an example.
So the callback functions are at the distributed computers, or is it at the server? Like the callback function gets called by the cashier, or does it get called via I think the cashier and then the server are two different computers, right?
Yeah. So you are simulating a distributed system, but you're not actually distributed.
Okay,
so we're using a single machine to simulate a distributed system.
Okay, thanks.
You could, in theory, parallelize and having the processing of different elements of different machines that's called parallelized discrete event simulation. It's hard. There's a lot of things that might go wrong. People might have tried it. This is not what we're going to deal with today. But, yeah. So imagine all of this is simulated within one machine. Okay. So now we're going to we'll see how to do this on Julia. Okay. I have posted on Zulip the pointer. Yeah.
One last.
Yeah.
In between events, what are we doing?
Sorry, can you repeat that?
In between events, what are you doing? Are you still keeping track of the dynamics of the system, or are you just looking at the outcome after one event, doing the callback, and then looking at the outcome after the next event that's scheduled by the scheduler?
In between events, if there's no event in between, you're just going to skip that whole thing because nothing's going to change in the state of the system. So you can just go from when you finish executing the callback for that event, you just update your time and you're going to just jump in the blink of an eye to the following event when it fires. Because all the state update for the system happens in the callback of the event. So once you finish handling that event, you can just evolve time up to the next event in line. Yeah, so that's how you do it. Okay, so on Zulip, you should have, you see the GitHub link, you can download this whole package locally. Alternatively, you can just start coding on any Julia package you have locally installed on your machine. And you should just add these packages here we're looking at. Specifically, this is ConcurrentSim. And this is our discrete event simulation package for Julia. And there was a couple of people that said they would have worked with discrete event simulation before. If you were doing that in Python, you might have encountered SimPy. And this package here is the exact equivalent in Julia. So SimPy Python, ConcurrentSim in Julia. Whatever we're going to learn now about this package, basically almost one-to-one applies also to Python. Okay, so the first thing we want to do once we start modeling our simulation is create a simulation object. So this is pretty straightforward. So at the beginning, we haven't run the simulation yet. So at the beginning, we have simulation time starting at 0. There is no active processes, no events, nothing. But it's empty. So say what we're going to model here is let's imagine there is a philosopher that's sitting on the grass, and he's going to wait for a few seconds, and then after that many seconds, he's going to have a brilliant idea. So our event is when the philosopher gets the idea. So we define it as an event, right? And we pass the simulation as an argument. Let me snooze Copilot here, because we don't want it. How do I snooze it? Okay. Okay, so we have our event. So now if we inspect the state of this event, it's idle because we have defined the event, but we haven't told the server that it should schedule this event at some time in the simulation. So what we're going to do is we're going to schedule now the event. So we're going to schedule the idea event at time, I don't know, 42. So now if we get again the state of the idea, it's scheduled. So it's in the timeline at 42. Now what happens usually when you do your own simulations is this time, the time of the event, it might be a random variable. Because for example, you don't know how long it will take for a user to get served by the cashier, right? It depends on the length of their cart. So you just maybe want to sample from a probability distribution. So instead of a fixed number here, you might have normal something or geometric something. That's pretty common. So now we have our idea. Now what we need is the callback. So what happens once this event fires? So we're going to have our philosopher tell us his idea. So we're going to have a first callback. That's simply, we're just going to print something. And he found the meaning of life, and let's define another one. We can have more than one callback, and we just print. Instead of this, let's just print actually live. Let's evaluate live what time we are in the simulation. And we do this through the now function that has to be called on the simulation. And you can get the simulation by calling environment. We can just use sim, but we can also use environment of event. So you can, if you have the event, you can forget about the reference to the simulation. You can get it back from using environment. Okay, so we have our two functions. Now we mark them as callbacks for the event. So we use the macro callback, F1 for idea, and 1 for idea. And the same for F2. And if you have multiple callbacks, I think they will be called in the order you define them as callbacks. That should be deterministic. All right. So we run the simulation. When you run the simulation, you can either just do run simulation, and this means that the simulation will run as long as there are events in the queue. So if the simulation in theory might go on forever if things keep happening. You can also specify a maximum time, say 100. It means that the simulation will go on up to time unit 100. It's totally up to you to interpret that as any time unit. You can interpret those as 5 picoseconds, microseconds, seconds. It's up to you. So we run a simulation, and we see here that the meaning of life is 42. So our philosopher had his idea, and the idea was processed at times 42. So this is what we expected. Okay. Now, imagine using this exact API to simulate an entire quantum network, to simulate, I don't know, a complicated, a full computer architecture. It would be extremely painful. Because we're working at very low level. We really are bare bone here. We would have to define all our kind of events. I would manually wire them with callback functions. It would be, it is powerful. Like you can do everything with this, but it's painful. So what we're going to do now, we're going to look at a slightly higher level API that's usually easier to think of in terms of how the design simulations. It's going to be easier with the following API. And so this redefinition works as follows. So instead of thinking of discrete event simulations as events that you manually schedule in the queue, you think of the simulation in terms of the actors that actively take part in the simulation. So in our philosopher example, that's pretty simple. There's only one active participant, active party in the simulation, that's the philosopher. So our only actor will be the philosopher, and the philosopher is the only dynamic component in the simulation, the only thing that can create events. If we think about our supermarket, the actors would be I can use it, I can imagine having the queue as an actor that generates the arrival events. I can imagine having each cashier being their own actor doing things. And they might be all instances of the same struct, of the same actor. So we're going to rewrite the philosopher example using this actors paradigm. And I'm calling them actors, so I think it's more intuitive, but the way the term that is used within ConcurrentSim and SimPy is process. So we're going to rewrite the philosopher example using processes. So specifically, an actor within ConcurrentSim is a resumable function that's called a process. Are you familiar with the concept of a generator in coding? No? Okay. So a generator is a function. So usually a function returns a value, right? Generators are actually basically they become an iterator. Because instead of returning a function, they yield a value. Instead of returning a value, and that's it, they yield a value, so they return a value, but then they can continue executing. So if you call them if you call the same function multiple times, you're going to get many values, many return values. So you can iterate over the function and get the yielded values one after the other. So you can use the function as an iterator. And this marker here, resumable, this macro, tells you exactly that this function will be a generator. And we're going to understand why in a second. Resumable function, so philosopher. And we have to pass a reference to the simulation as an argument. You can also pass more than this, but this is usually at least this a reference to the simulation is usually what you want to give as an argument. So logically, what do we want to do here? How do I? Aha, got it. Nice. Shut up. What do we want to do here? We want to wait for 42 seconds because that it's easier to think this way because this is what the philosopher does. So we're going. What does the philosopher do? he waits for as long as he's waiting for until he has an idea, and when he has an idea, it will, I have an idea. Okay, so we are going to yield, which means return in terms of generator functions. So I yield a timeout, and timeout function wants the simulation and how much you're going to wait for. Then after, so this means that if it was like this means that the first time you call this function, it will stop its execution here and return this timeout. And this is an object. So the simulation engine in ConcurrentSim will be in charge of calling this function once it sees that it's yielding a value. It reads this value. This is some timeout object. The simulator engine will understand that it has to wait for this amount of time once, and then it will stop the execution for this function for that amount of time, and then call the function again. So the rest of the function will be executed after it has waited for this amount of time. If you want to see it in terms of the callback functions that we were talking before, the way you do implement this using the callback API is at the beginning of the simulation, you call this right away. So you go up until here. This creates an event in time at time 42. Okay, and the way the simulation engine as a callback for this specific event here, as the callback for that is calling this function again. It's having this function progress more after this yield here. So this is how this translates to the callback. So callback API. All right, so all this was to say that at line 26, now after yield, now here, I know that I have already waited for 42 seconds. So here I can just simply, print the things, right? So I'm just gonna call my printers from before. Actually, I'm gonna copy it here. I don't have to pass the event anymore because I have the environment directly. Environment simulation, they're the same thing. Okay. So we create another simulation. And now what we do is, now this, for now, that is just a resumable function. The resumable functions have meaning even outside discrete-event simulation. We have to tell the simulation engine that that resumable function is a process. It means that it's an actor in the simulation. So the way we do that is macro process philosopher called on sim. There we go. Now we run the simulation, and it should have the same exact outcome as the simulation before. And there it is. The only difference is that we implemented the same thing with a different paradigm using processes. And this is the abstraction level that ConcurrentSim works at. And still, this is pretty bare bone. Working with processes, it's like a bare bone way of designing discrete-event simulation. And it's in the philosophy of this package here. So whoever wants to build more advanced, more higher level discrete-event simulations that have a lot of APIs and shortcuts, such as what we're going to see in this afternoon, will build on top of this. But for the purpose of this package specifically, we're going to work with processes for the rest of this morning. Okay. Yeah, so let's see a little more about what we can do with these processes. So. Let me just copy this. Let's read this together. Let's have another simulation, and let's have this process here. So this process here, what does it do? We define two events, a timeout at time 10 and a timeout at time timeout after 10 seconds and a timeout after 20 seconds from when they're called. Yeah.
Does it break if you swap the order of them?
No. No. So if I yield a logical OR between two events, so timeout, this timeout and this timeout, this yield will fire when at least one of the two events has fired. All right. So this means that this yield we will keep executing once either event 1 or event 2 has fired. So can you tell me, what do you think once we are here, once we print this line 40 here, what time are we going to see in this print? Assuming that we start from 0.
10.
10, exactly. Because at time 10, event 1 fires, so we're going to see 10 here. And that's why it doesn't matter. So if it was 2, it would have, the other one would have fired, and it's at least 1, so that wouldn't matter. So now instead of the OR operator, we use the AND logical operator. So if we yield on event 1 and event 2, it means that both have to fire. So if here we are at time 10, what time in the simulation you think will be once we print this?
Uh, 200? Is that?
210, because you were already at 10.
The first one, yeah.
Yes. It's not 310 because you don't wait them. They're not in serial. They're not sequential. It's not like one after the other. Both of these events are scheduled together. So one fire at 110, the other fires at 210. By 210, both have fired. So you go on. And so on and so forth. So now this is pretty readable. Any of is basically an OR between all of those pairwise. All of is a logical AND between all of the arguments that you pass. So let's run this just to see that we were right or wrong. Hopefully not. And yes, so this is what we were expecting. 10, 210, and then whatever. Okay. So now we're going to do a little, we're going to go on a very brief tangent because we're going to see together that, so I want to make clear something, that is simulated time, yeah.
Sorry. I guess my question is, in what order exactly are we executing things? Because so it was confusing to me that the next set of events were scheduled only after the first yield was done. So does doing an add yield pause time, or at least pause the code?
So you can see it as follows. So let's go back to the simpler case. So once you call this, you're scheduling an event in time, the timeline. And you, as a callback for that event, you're basically setting, okay, as a callback for that event, I'm resuming the execution of this function.
Sure.
So so you put that event in the timeline, the server will schedule that event at time 42. At time 42, you resume the execution of this function, and that's when you print this.
Correct.
This is all that's happening here.
Perfect.
And these things get more intricate when you have multiple processes, in which we're going to see that in a second. There are many processes that interact with each other. So when a process wakes up, resumes, it might wake up. It might, as a callback, it might wake up even another process, and you can have a lot of complicated interactions. So that's how you set up multiple parties interaction.
I see. So the reason in the other function, we had 110 instead of 200 is because you renamed the first event, right? if it was called event 3 and event 4, would the scheduler just schedule all? Would it just schedule something at 10, 20, and then at 100 and 200?
No. If I call this, I mean, if I call this event 3 and event 4, yeah, I can do this. It's gonna be exactly the same. It's just I'm reassigning variables. Once we are after this, event 1 and event 2 have been scheduled, processed, and called a callback, so they are done forever. We could delete those variables. So I was just reusing the same variable names. So those events are already being processed. So
Okay.
who cares?
Fine.
So
I understand how you.
is the second argument like the time difference then, not like the objective
Yes.
at this time?
Yes. So the second argument here is how long you want to wait for from the moment you call it. So if
You don't
now
call
you're
it.
at 10, you want to wait for 200 more seconds.
And you call it when you do at the end of the at yield, it gets,
So the yield, so this is an event. It means I want to wait until the earliest timer fires. You schedule that event. The scheduler understands that event will fire at time 10. So that's when the scheduler schedules that event. And as a callback, you move on with life, and you go afterwards. Make sense?
Sorry.
Yeah.
When you hit the yield of 100 and 200, it's gonna print. Will it print 20 before it prints to 100, 200 or not?
It prints 210.
Okay, but does 20 ever get printed? So I'm asking.
Pardon?
Does the 20 ever get printed?
The 20, no. The
No.
20 never gets printed, no.
Okay.
Because I mean, there's nothing in the code that you're never
You never yield
printing
it.
now. Yeah, you're never stopping at that time in the simulation.
Oh.
Because there's no event that fires at time 20. Because you fire here and here is time 10, and then 20 is forgotten forever. There is no event scheduled at time 20 because the only event is this event here. It's an OR between the two, and the server is smart enough to understand that happens at time 10. So at 20, nothing happens.
it has to be more complicated stuff. Like,
Okay, now I'm gonna copy a bunch of things. And we go over them together. So yeah, what I want to show you now is that one thing is the time that's evolving with the simulation, which is what we have been printing here, right? So time, that's totally, almost entirely uncorrelated with wall clock time, with the time you spend waiting for the computing to be done. So those are two completely different things. And usually like the time, the value, the magnitude of the simulated time has nothing to do with the time it takes to run the simulation. The only thing, as a rule of thumb, what determines the time it takes to run the simulation is the total number of events that are scheduled. So if you schedule 1 million events, whether they happen in the span of 1 nanosecond or of simulated time or in the span of 10 million years, the simulated time that it takes, the real time it takes you to simulate those 1 million events will be the same. So that's how these two quantities are correlated. And what we're gonna do now is to see this principle, okay? So what we're gonna do, we're going to have a very simple process. It's a simple timer that basically waits for a given amount of time and then returns. That's it. It's a very simple process. Then we're going to define a function that basically times that calls the timer, instantiates it as a process. So basically, this function here runs a single simulation where there is one timer that waits for a given amount of time, and it evaluates the time you wait, like the time it takes for that simulation to run, the real time, and then returns that value. And here I will not go over this, but you basically collect a bunch of samples and then we plot them. And then now we're going to see how So what we're going to do is we are going to sweep over the time that the timer waits, the simulated time, or we're going to show you that the actual real time it takes to simulate is basically independent with respect to what value we set here, because it's always still going to be one event. Oh, the plot is popping up here. So as you can see, there is no correlation. There is no like simulated, it's not like as the simulated time goes up, you also see runtime going up. It's random, right? And it depends on what other processes are in your laptop, and because it's only going to be one event that you're simulating. So there is no real correlation. And that's all I wanted to show you here. Okay. All right, so as I told you, things get a little more interesting when actually there is more than one process that's interacting with each other, because that's what a distributed system is. There's multiple entities that are interacting. So what we're going to do now is the hello world of discrete event simulation that is called ping pong simulation. So you have two actors, ping and pong, and they just play ping pong. So one pings and the other pong in return, and they go on ping pong, ping pong, ping pong. So we're going to write a process, the code for a process, that is going to be shared between the ping and pong player. So we have our environment. We also have to pass, because ping will print ping, pong will print pong, so we need to pass them the word they have to print, right? So we are going to say favorite word. And I also want to specify who their partner is. We'll see later. All right, so what does the ping pong player has to do? So we are going to be in a while true loop because we want this to go on forever. But at every iteration, we are going to have a reference. Yeah, so we're going to have an accumulating message, because we're going to print the whole sequence of ping pong, ping pong, ping pong every time. That's going to increase over time in length. So we have an accumulating message that takes your favorite word, right? Now we're going to do something that will look a little alien, and it's the following. So we're going to put a yield, and we're going to basically time out. So we're going to time out forever. We're going to wait for an infinite amount of time. What this means is okay, I'm going to put this process on hold until someone interrupts this process and forces this process to resume its execution. And we're going to see how we're going to do that in a second. So if we, it's like standard to do this in ConcurrentSim using try-catch syntax. So if you're in the sketch, it means that you have been awakened out of your will, basically. You have been awakened not because the event fired, but because someone woke you up. So if you're in this catch clause, you're going to look at your partner. if your partner is nothing, you're going to set it. So we're going to use a short circuit, do that. And you see the E is the exception. And so it means someone woke you up, right? So you want to know who woke you up. That's going to be another process. So if you use .by, it means you're referring the process that woke you up. So your partner will be whoever woke you up. Now, the exception also has a cause, like why were you woken up? Why you were awakened? And the cause, we imagine it will be, it's up to us, right, what to write in the cause. And we are going to imagine that whoever wakes someone up will put the list of ping pong so far. So what you're going to do is, again, we check if it's nothing. Otherwise, we basically append everything into the accumulated message. Okay. And yeah, the reason why I instantiated accumulated message at the beginning is that in the case in which this is nothing, this would otherwise be non-defined, and that would be an error. Yeah.
On that second line, that is nothing e.cause and accumulated message. Don't you want that to be an or?
Sorry, which line?
Line 111. Should that be an or operator?
Oh, yes, you're totally right.
Yeah, if it's not nothing.
Yeah.
Yes.
Thank you. And okay. And now when we are here, we are the ones that have to wake the other one, right? Because now we have been awakened, we have created our message, so now we have to print our message and wake up our partner in return, right? So that's what we're going to do. So we're going to print but let me copy it. Easier. So we are going to print the accumulated message so far. And also we're going to print what time we are at, just to take a look. Then we're going to wait 1 unit of time just to have time evolving, because so far nothing has had any time evolution in the simulation, right? And after we wait for 1 second, we wake our partner. And that's how we do it. You yield and interrupt. So that's another built-in kind of event in ConcurrentSim. You yield an interrupt, you specify who you want to wake up, and the cause. So this is going to be the by and cause of the exception that's caught by your partner. So if I were to do this now, if I were to run this, so I create a simulation, I create Ping and Pong, Bob and Alice, Alice and Bob, and I run this. What do you think we're going to see?
A lot of ping pongs.
Ideally, yes. What actually we're going to see is nothing. And I'm going. Yeah, it printed nothing. Does anyone know why? Yeah.
don't we need to start the chain by interrupting one of the
Yeah, because
layers?
exactly. Because at the beginning they both started waiting infinite time, right? So no one gets woken up if you don't do it at the beginning. So we need some starter process that wakes up the first player. I mean, there were other ways of implementing this. This is just one choice for me. You could have had a if clause here. If your favorite word is ping, then you don't start by waiting, but you start by interrupting. But this way, the code for both is exactly the same. So I'm just gonna copy it because it's not particularly interesting. So I created one more process. That's the starter that wants the environment, and it wants to know who the player that starts it is, and simply yields an interrupt for that player. So now we add one more process to the simulation. That's going to be the starter. So what's it called? Start sim. And we want the simulation, and we want to start with Alice. So now ideally we'll see a lot of ping pongs. Let's see. There you go. We might have run it for a little too long. But yeah, at the beginning you see, start with ping, then ping pong, then ping pong ping, blah, 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 blah. Okay. All right. As you can see, interaction is still a little painful, right? I say it's not very smooth API. So it's not, in production, once you model very complicated systems, again, this is not going to be usual unless what you simulate is very simple. This is not going to be the API you want to use. I personally don't like this catch mechanism. It's a little like unintuitive for me. And what we're going to see next is a way more natural way of having interaction within processes, and that's what I would focus on. But even then, this whole ConcurrentSim package is supposed to be a barebone discrete event simulation package. And usually what you're going to do is going to work with other packages that use this under the hood. But it's good to know what's happening in your code, because that's how you're going to know how to make things better and more performance efficient.
Can you show the start sim?
Yeah.
Line again?
I don't know if you noticed, but if you open lecture.jl, you should have all this code in the GitHub. So if you just want to copy and paste it and run it with me without having to type it, you're welcome to. It's up whatever works best for you. Okay. All right. So as I was saying, this direct way of communicating by literally interrupting a specific process, it's a little clumsy. Usually a much more natural way of having interaction is some sort of indirect communication. So say, and it's by sharing limited resources. So for example, imagine two processes in your system that try to write on a file, on the same file. They both try to lock writing access on that file, and that's where contention happens, and they have to synchronize. So one has to go before the other. So they both try to lock a resource. Only one of them will get access to the resource. It will write, then will release the resource. The other one then can get the lock on the resource, write the file, save it, and then they're done. And they never interacted with each other explicitly. They don't even know about each other, but they indirectly interacted because they were waiting on the same resource, and they have to wait and be serially executed sequentially because they couldn't do it at the same time. And this is what we're going to do next. So we're going to see how to set finite resources and have processes compete for those resources in a polite way. So the abstraction we're going to implement is the abstraction of a group of friends at a beach that for some reason they want to dig a very deep hole in the beach. So they have a bunch of shovels, say 5 shovels, but there's like 20 friends. And the way they do it, that only 5 friends at a time can work and dig, right? They can dig for some amount of time, and then they have to put back the shovel and rest because they're tired. So every friend will be an actor, and they will try to get access to a shovel. And when they do, they shovel for 5 minutes, and then they put the shovel down and rest for 5 more minutes. And yeah, so let's try to set this up. And this is common practice. So basically, we are going to define a structure that contains the state of our simulation. So if this is going to be a reference, a structure that contains the current state of our beach. So it tracks down how deep the hole currently is. It tracks down how the shovels and who has the shovels. So we have our beach, and it's mutable because we dig the shovel. So we want to update the value of how many inches we have dug. So that's going to change over time. So we're going to have for sure a reference to the simulation.
I have a question.
Yeah.
Are we thinking about this as if like the 5 friends get tired at the same time, or is it possible for like one friend to be tired before the other ones?
Yeah, so it depends on how you model it. If you have, say you have 2 shovels. You have 2 shovels. And if you start the simulation and you have 3 friends, say, right? You have 3 friends. If you start the simulation, only 2 of them will get access to a shovel at the beginning. If the time after which they get tired is a constant, they will get tired at exactly the same time. But still, they get tired at exactly the same time, so they will go resting. So will start resting. So there are going to be 2 free shovels, and this guy then will take 1 shovel. And for the following 5 minutes, 1 shovel will be idle because these 2 guys will be resting. So I guess a proper way of doing this would be to randomize the time after which they get tired, so you can see some variability. Otherwise, yeah, weird behaviors like what you said might happen. Yeah, not sure. Yeah.
If you schedule 2 events at the same time, what does the simulator does? Does it choose arbitrary one of the 2?
Yes. You don't have any knowledge on which one is going to be called back first. But what you know is that that's going to be determined. Like whatever order it is, every time you run the simulation with the same seed, it's always going to be the same order. But you don't know what that order is a priori. But ideally, if you design your discrete event simulation well, the order shouldn't matter. You should design your simulation so that the order of how you process concurrent events shouldn't matter. Okay. So we have a reference to the simulation. We want to define our shovels, and we were going to model the shovels as a resource. And this is a built-in type in ConcurrentSim, and it models a resource of which you have k available instances, and processes can try to get a token from the resource. And if there are no more tokens, the process will have to wait for a token to be available before the process can move on with life. And we're going also to track how much we dug, right? So amount shovel. And then I'm going to put a constructor. Okay. Now we write the code for a shoveler. So it's very simple because the shoveler waits for a shovel to be available, works for some amount of time, then updates the shoveled amount shoveled variable in the mutable struct, then rests, and then go start back the loop, right? Sorry, he has to put the shovel back also at some point. So the shoveler will want the simulation. It will also want to know what the pitch is. And let's say we pass those values as the work time, as the rest time, as two arguments, so we can vary over them. Work time and rest time. So going as we said, so we are in a while true loop, and this is very common to have while true loops. So we try to get a shovel. So we yield, because we want to generate an event, and the event is we're able to get a shovel. The way we say it, it's get what? I guess let's do this. I define a function shovel from pitch. Because I really don't like using the beach.shovels in outside the struct, so I always like to define this sort of helper functions. So we get let's do this though, shovels. We try to get a shovel from the shovels. So we try to get how many? One, because we only need one. So we try to get one shovel from the shovels resource. So once we are done here, it means after this yield, we have gotten a shovel. So here now we have a shovel. So now we yield the timeout. That means that basically we wait for as long as we work. So after this timeout, we have worked for that amount of time. So time has evolved. So now it's time to rest. But first, we update the shared amount shoveled variable. And we just put it equal to the amount of time we worked. Forgetting that they have different units. Who cares? And now we rest. So we yield yet another timeout. I guess before yielding another timeout for rest time, we need to put the shovel back, right? So here we yield again. And now we yield the put. Well, we're going to put one shovel back into the pitch. Okay, this should be all for the shoveler. I think it's pretty intuitive, right? Once we work in terms of actors, processes, like you just need to think of what is that entity doing in the simulation. That's how you design it. What are the other I mean, that's all. The shovelers should be the only actors in the simulation, right? Because the rest is just the shared resource they're competing for. So now we simply run the simulation. I wrapped it into a function just because then I want to plot something. So I'm just going to copy that. So let's take a look together. So I define a function that basically sets up the simulation and runs the simulation for some given time. And at the end returns how much we shovel in that simulation. Then what we're going to do, then we pass both the number of shovels and the number of shovelers. Then what we're going to do is we're going to sweep the number of shovelers between 1 and 40 run the simulation for always the same amount of time, and then print the total amount of sand units we have dug as a function of the number of shovelers. So this way we're going to see basically when is the crossing point from when the shovels are the bottleneck and when the shovelers are the bottleneck. But if there are very few shovelers, then the shovelers are the bottleneck. If there are many shovels, then the shovels are the bottleneck. And where you see the crossing point, because as you increase the number of shovelers, you're going to see the number of shovel sand increase up until some threshold. So you saturate there because then the shovels become the bottleneck. That's what we expect to see. And we are plotting that here. I should run from here. Yes.
Yeah.
Grab it. And there we go. At 20 shovelers, we see that they become the bottleneck. So if having 30 or 40 shovelers doesn't make a difference because it's the shovels that are a very scarce resource. So there's always going to be an available shovelers, but there's not enough shovels. Yeah.
2 questions. So I assume this plot, of course, will depend on the ratio of work time to rest time,
right?
Because it needs to be scheduled. Okay. And second, you said this earlier about concurrent events and having no order over how to schedule them. There seems to be a very obvious race condition over here where if you end up scheduling someone to pick up a shovel at the same time as someone else dropping a shovel,
yeah,
then there's going to be a conflict.
That is correct. But the thing is, that is correct. The thing is, though, this is distributed. The way you code this is as if it was distributed, but actually it's going to be run serially on a single CPU. So there is no race condition in the sense of what you were saying. Like the update. Let me check. Let me go back there. Zoom in the middle. Okay. Wait. My screen share is failed. Oh. Yes. Okay. So if we go back here, because this is like if you take a CS class, this teaches you that this is not a single instruction in the CPU. These are 2 instructions because you want to read the variable, then update it. And if someone interrupts the execution in the middle between those 2 and something else happens, you might have a race condition where you have inconsistencies, right? But since this is not actually run distributedly, you have, so everything between this yield and this other yield happens at the same time. Okay, so once you start running this, there is no one that can interrupt you because it's run serially. So you can implement this and get away with it, but it's good that you are aware of it. And this is also one of the reasons why having parallelizing discrete event simulation it's hard because you might at that point incur in exactly that kind of problems.
So I guess, okay, I had a slightly different scenario in mind. Pretend you had 0 shovels in the bank, in your resource, and the scheduler scheduled 2 events simultaneously. One is someone dropping a shovel, and the other is someone picking up a shovel.
Right.
Now, depending on which order you execute it in, it's going to either be possible or not possible, right? Because if you schedule the dropping slightly before the picking up,
I see what you mean.
Possible.
So this goes back to the question he asked. So so the thing is, it's designed so that it's independent, like that it's smart enough for it to not matter. Okay. Because if say let's go with both orders. Right? So there's no shovels. Someone tries to get 1 shovel, and he waits there because there's no shovel. So that guy is pending. It's waiting there. The guy later on puts a shovel back down. The server. Oh, there's a new shovel. Let's wake up whoever was waiting on that shovel. And he goes and wakes up that guy, gives that guy the shovel, and the guy wakes up. Okay. Everything works. Vice versa, if you put the shovel first, good. Then the guy arrives, there is a shovel, so the guy takes the shovel and goes on. So both cases, simulation basically
Okay.
behave the
So
same.
we just have to make sure to have these kind of fallbacks.
Right, you have to be sure the way you implement it that the order won't matter. And if this is an example of something that works properly. But if you just stick to these shared resources, usually they don't incur in this kind of problems because this is like already set up for you so that it will be well designed.
Okay.
And how about we take a 5-10 minutes break and then we finish off with ConcurrentSim. So let's be back in 32, 33.
He did say he didn't have his picture. Yeah. You should focus on. I've never heard someone say shovel so many times, just like in half an hour. Shovel. Shovel. Shoveled, sand.
In the sense that you have smart.
I do 20 frames.
Jump to the next thing, calls a callback, jumps.
Okay, I was gonna ask you guys, cause I feel like it's super normal.
Like puts down the shovel.
Oh.
Not even building sandcastle, just hole, and then I stand in the hole and then drive how deep it is. So this is not like a universal, like, you didn't grow up going to the beach and digging really deep holes, just have
I
a deep
think he
hole.
actually was saying that the
Just start digging
simulator,
and then
the
turn
server
selecting
is
what
smart
it is.
enough to say, like, if it schedules two things on top of each other, two events at the same time step,
Has this
then it
weird
doesn't
phenomenon.
matter which
What
callback
are you
comes
trying to
first,
get to?
because if the shoveler puts down the shovel first, and then the person picks it up, then it works. But if the person goes to pick it up first and there's no shovel,
There's a break. Let me.
I've never
says
used
this
it
person
myself.
was waiting for a shovel. The person goes to sleep, and then the shoveler puts the shovel down. Simulator says, "Oh, there were concurrent events here. There's a shoveler waiting, and it wakes back up."
And then I just had a text, when there's a break and you can get me, he's like,
He's saying that the server is smart enough.
I saw the video in the book, so I just didn't do that.
Yeah. Oh, nice. What
But you know, this one for the
But,
project.
Right.
are you PhD? Like, what's happening?
I'm from like.
At least the Trojan was.
Oh, that we did. I graduated or something.
I don't remember. I would just do it by myself.
No, in AV had it. It was.
This is because like I work with PME as well. This is because I work with PME as well.
I don't know.
You graduated.
But he said the movie is
Iliad
about.
and
Well,
Homer
like,
and all
just
this.
as-
I've heard, but that's not something
Yeah,
that
I graduated back
give
in
you
December.
details.
I
Yeah, but
had
I've heard his name.
What's your, yeah, what was
Yeah,
it?
Trojan war, the Trojan horse, all this.
Dude, I think you were my, you
Really enjoy
right?
yeah.
Yeah,
It's all right.
There's a movie.
yeah, I was in GP.
Yeah,
I
you
just
don't know?
graduated,
It's
Christopher
the
Nolan.
biggest
Oh,
movie.
that
John Joseph.
Oh, wait, you have Berkham.
What happened?
You get to use Berkham.
No, I tried to go to your office hours sometime, but you weren't there. I didn't. I swear, I went one time, I was like, I'm gonna meet them the first week. I was like, I was excited to meet you. But, yeah, I see.
No, but like even the cash, like.
Yeah, I think the semester just got so busy. I switched to like the C++ course, like.
Because it's based on the translation, it's based on translation.
Not saying that.
I mean, it uses modern technology, so that it's easier for us to be obviously, because otherwise I feel like if you use the IDA, I think it's clear, or you later then you process it again. So we use the same kind of thing, like he says that,
Sure, we're good friends.
like he doesn't say fuck, and then they will say, like, and he's matching.
Is that the kind of thing? Is that what you're doing now?
Stuff like the one,
I'm like-
the most like ConcurrentSavory, you think, or does this guy, that's
Oh.
for real, and slide his team.
Personally distributed company.
Oh, cool.
HPC.
Oh, nice.
I'm also with PME, where I
The RSS with Boston accent.
All right, it's 35, so let's get back because we have a lot of work to do. And not a lot, like normal amount of work. Okay, wait. So we have taken a look at a resource, so shovels, finite amount of shovels. Now we're going to take a look at a different kind of shared variable that's useful for a different kind of modeling. Both of these will be helpful for you in modeling different kind of phenomena. So what we're going to take a look at now is called a store, and it's a different kind of shared resource. So the abstraction we're going to work with now is that of a grocery store, but it's not in terms of the queues, it's in terms of what you're going to buy. So imagine there's a bunch of customers, of shoppers that want to buy fruit, and every customer arrives and they are hungry for a specific kind of fruit, and they can only get the fruit once the fruit is available. So we're going to have shoppers that get it's kind of a wild grocery if you think about it, because usually people don't just go and eat the fruit right away, but it's what it is. So they arrive, they wait for the fruit, they eat the fruit. If the fruit is not there, they just wait. And there's also going to be another set of processes of actors that are like the people that refill the store with fruit, right? So we're going to have the shoppers, we're going to have the suppliers. So let's see how we can model this kind of interaction here. So let's first define some decorators to formalize our fruit types. So I define the abstract type fruit. And it's simply a decorator. And then we have, say, we have apples and oranges. So we have apple that is a subtype of fruit. And it has no fields, it's just a decorator. And we have orange. And we have our grocery store. We imagine it's Whole Foods. That is a store of what? A store of fruit. Wait, first I have to create a simulation object. So the Whole Foods will be a store of fruits, and as an argument, it wants a reference to the simulation. So this should all work. Up. Yes. So what does this mean? So a store of fruit, it's another kind of shared resource, but it's a little more elaborated, a little more articulated than a simple resource, because a resource type is something you put tokens in and you pick up the tokens. So one element type. The store, you can put items of different types as long as they are subtypes of the type that you specify for the store. So they have all to be fruits, but they can be apples, they can be oranges. And when you try to get something from the store, you can specify what kind of fruit you want to get. So it's basically a database. You want to filter and get something that's in the database that's only of one specific kind. So yeah, let's get into it. We will just basically now write down what our shoppers look like. And again, it's going to be pretty straightforward. We have our environment. So every shopper will be initialized with a specific kind of fruit they want. We assume that they always want the same fruit. And to make things a little more spicy, we put that as a function. Every time it can be, in theory, it could be a predicate. They could, if there were apple, oranges, and bananas, they might want oranges or bananas. So it can be not just one single type, but it can be a predicate function that returns true for multiple types. So accepted fruits will be a function. It takes as input a fruit and returns a Boolean. And then we want a reference to the store. Fruit. And okay, what did I do here? And we also want to specify some time they will wait after they have eaten before they get hungry again. So it's snack time. Oh, oh, there it is. Okay. Sorry, this is not process, this is resumable. Okay. Now, let's think about it. What does a shopper do? So they arrive at the store, they try to get the fruit they want, they wait for it. So let's start with that. Again, like, give me your question before about randomizing things. Let's do it right now. Let's randomize when shoppers arrive at the store. So shopper starts at the beginning of the simulation, but it will only enter the store after let's put it in a loop. So every once in a while, they will get hungry and enter the store. So while true, and so at the beginning, they'll wait for some randomized time and then enter the store. So let's do that. Arrival time is going to be a random variable that's modeled as a normal distribution. That's really up to us. With average snack time. I could have put just, instead of randomizing, I could have just put snack time if I wanted. But it's just to make things a little more interesting. Then we wait for that amount of time. And then we print the fact that we arrived. All right. Now we have to yield what? We want to get a fruit, right? The fruit we want. So we get from the store. And now we have a second argument. And the second argument is not a number. It's not how many fruits we want us to get. It's the kind. It's the function that filters what kind of fruits we accept. So we pass accepted fruits here. So to retrieve the fruit that we actually got from the store, this is the way you do it. You get the fruit. The fruit is equal to what? To value of purchase. Sorry, let's do this. I need a reference to this. So I will do the nope. Purchase equals this. Oh God. Why? Yes, store accepted. Okay. And then we yield purchase. Okay, this is better. And now we get value of purchase. Okay. And then we print it. We don't need to do anything else with that. Okay, so that's all. And after this loop ends, it's nice because you go back to the beginning and you wait while you eat your fruit and before going back to the store. So this is all the shopper does. Now we have to model the suppliers. The suppliers is even simpler. I'm just gonna paste it from the solution here. There you go. So what the supplier has basically the same parameters, except now we have to specify how many fruits they put back in the store, and the time, the period, the average of the normal random variable that we sample when we determine how often they come to the store. So they arrive at the store every sample of this normal random variable. Then they wait for that amount of time. And then for each fruit in the supply amount that they are refilling, they put a fruit back into the store. And then they print what they put back. So that's all. And we pass as an argument the kind of fruit that they are putting back into the store. Okay, so here now I'm going to before running it, let me show you something important, which is the following. Usually when you do random simulations, you want to run several times with the independent seeds, right? And then collect the average, compute your confidence intervals. That's how you properly do things. And the way you set independent seeds for your simulation is one way, at least, is using random, and then you seed random. And say we specify 1, 2, 3, 4. Okay, let's run whatever we have. Bloop, bloop. Okay, we have now seeded random. So if we run this code k times, we will always get the same exact results because it's randomized, or we fix the seed. So it's always going to be the same. Now let's say we instantiate a bunch of shoppers and suppliers. So I'm creating a shopper that filters for apples. This function is equal here, it's a function generator, it returns a function. So it's a function of filters for anything, it returns true if what you're passing the function is an apple. The store is Whole Foods, and this I think was the snack time, yes. So we're gonna have 1, 2, 3 shoppers, of which one wants apples, one wants oranges, and the other one wants anything. And you see this function here is anonymous, so it always returns true, so we will accept any kind of fruit. And the snack time of this non-picky customer is a little lower too. And then we have 2 suppliers, one for oranges, one for apples. So pretty straightforward. And we run. And hopefully it will not break. Okay, nothing because we did, I did not run the code before. There we go. Aha, so let's see. So in this specific run here, we say, see, customer arrived. They both arrived and they are waiting because nothing is in the store at the beginning. And the supplier delivers oranges, and then the customer can buy an orange, and so on and so forth. Anyway. All right. Well, this basically concludes me going through ConcurrentSim. So we have all the tools we need to model anything we want right now. What I feel like it's most important for you is to consolidate what we saw, because I know by experience that if we don't get our hands dirty, we will never actually learn how to deal with this sort of packages. So what I'm going to do now, I'm going to show you an incomplete example. So this is, I strongly recommend that you go online and download the file. It's called repeater exercise from the GitHub repo I gave you. And this is we're going to model a quantum repeater, but I'm going to leave some holes in the code for you to fill in as an exercise for you. So before we get into that though, I want to know how many of you don't know what entanglement swapping is? How many of you don't know? Okay, a bunch. Okay, let's define that. One, because this is going to be useful for later too. So one of the main purposes of entangled network. So a quantum network is a distributed system in which user A wants to send some quantum information to user B, right? So any system in which there is transfer of quantum information is a quantum network. One very common framework in which we work, when we work with quantum networks, is to do that by distributing entanglement. So we want to distribute a Bell state and a bipartite entangled pair between user A and user B that they then can use to do whatever they want with it, included transferring a qubit from A to B using teleportation. However, the way you distribute entanglement is non-trivial, because you use photons to transfer entanglement, and you use fibers. Fibers have exponential decay, so you cannot have an arbitrarily long fiber. You need amplifiers, but you cannot use classical amplifiers because of the no-cloning theorem. So what people came up to is with what they're called quantum repeaters, and they work as follows logically. So say you have Alice and you have Bob, and your goal is to have a quantum memory at Alice entangled with a quantum memory at Bob. This is your goal. But let's say they're too far apart from each other. You cannot simply generate the Bell pair locally and send one of the two photons from Alice to Bob for Bob to store. This is not doable. The loss probability would be too high. So the way you do that, you put a quantum repeater between them. We call it Charlie. And what you do, now the distance between Alice and Charlie is half. So let's say now it's doable to entangle Alice with Charlie using there's many proposals for different entanglement distribution protocols. They're all probabilistic. So you're going to start a probabilistic process of entanglement distribution. Say there is a fiber connecting them, physical fiber. So you start attempting entanglement generation between Alice and Charlie until after k attempts, they succeed. So Alice manages to get entangled with Charlie. At the same time, Charlie was doing it with Bob. So at the same time, they are attempting entanglement generation, and they are uncorrelated, right? So maybe at attempt number K1, they are also entangled. So there will be one point in time where Alice is entangled with Charlie, and Charlie is entangled with Bob. Once this condition happens, so Charlie is going to have two qubits, two memories, one entangled with Alice, one entangled with Bob. Now, there is an operation called Bell state measurement that takes these two qubits that are local to Charlie, measures them out on a specific basis called Bell basis, measures them out. So these get canceled, traced out of the memory at Charlie. You collect the measurement outcome. You send the measurement outcome to either Bob or Alice for them to track. And once you do all of this, the result is that the qubit at Bob that was previously entangled with Charlie is now actually entangled with Alice's qubit, and vice versa. So this is how you stitch together link level entanglement into a single longer range entanglement. And you can iterate this to reach arbitrarily long distances. So this is what two-way quantum networks do. And this is what we're going to model now in the simulation. It's simple setup. So this guy, so the way what we're going to do now is we're going to model these three guys. And we won't really need to model Alice and Bob. We're just going to need to model Charlie. Charlie will have two qubit slots. It will wait for both to be entangled, and when both are entangled, it will do an entanglement swap. So what I call Bell state measurement here, this operation of doing the Bell state measurement plus sending the classical communication, this is what's commonly referred to as entanglement swapping. And that's because it swaps two local entanglements into a longer range entanglement. So yeah, that's, yeah. Yes. Yeah, you project these two qubits here into a bell bit. Yeah. And if you're familiar with the teleportation, you're basically teleporting the state of this qubit here, basically using these other bell pairs as a resource, or vice versa. Yeah, that's one other way of seeing it. Okay. So let's go, yeah. This is one LOCC. Yeah, so this is basically, so the way you distribute entanglement end-to-end is through an LOCC protocol. Yeah, this is an instantiation of an, that's also why I started off everything saying that's discrete event simulation is great for LOCC, because this is the kind of thing that are intrinsically discrete event dynamics. Because you have to wait for this to be ready, you have to wait for that to be ready, then you swap, then you send the communications, you wait for the communication to arrive, and it's all events in time. Yes, this is one instantiation of the LOCC paradigm, because the only quantum operations that happen here is the measurement that's done by Charlie on two local qubits. And then the rest was classical communications. Be fully precise, it's LOCC plus entanglement. And that's general, because yeah, the entanglement distribution protocol per se is not LOCC, because you're technically generating the bell state somewhere locally and then sending the two ends of the bell pair to the two nodes. So that is not technically LOCC. But besides that phase, everything else, to build on top of those link level entanglement, everything else on top of that is LOCC. Okay. All right, so let's go through it together. So let's look at how we model the repeater, just to understand what I have in mind for the simulation. So the repeater has two stores. And the store can only store link entanglement types. I could have used a resource probably too. So it's going to have a resource for the left memory and a resource for the right memory. And they're going to be, so what the process that's going to put stuff in there is the entangler process. So whenever entanglement is ready, it's going to upload something inside the left memory or right memory, depending which one of the two entanglements succeeded. We have a tracker that, like the same for the beach before. We are tracking how many end-to-end bell pairs we delivered to Alice and Bob, yes. And also we are tracking all the times at which we deliver end-to-end bell pairs to derive some nice plots at the end. Oh yeah, this is a constructor. Nothing too fancy here. Yeah. So we have this entangler process that I've left for you to implement. Now, what does this guy have to do? This is the guy there's going to be an entangler process running here and entangler process running here. So there's going to be two instances of those. And their goal is to toss coins until entanglement succeeds. And when the entanglement succeeds, they have to put something in the store. So this entangler here will, when entanglement succeeds, will put a link entanglement in the left store of the repeater station. When this entangler succeeds, we'll put something in the right store of the repeater station. So that's all you have to implement here, basically. And ideally, you want to randomize entanglement distribution. So let's try to implement this mechanism of tossing a coin until you succeed. Now, the repeater also, we basically already defined what it has to do, right? It has to wait on both left and right stores to be ready. So it wants to get from both. And when that happens, it basically deletes those qubits. We are not going to implement the actual Bell state measurement. We just abstract it away by saying, okay, we get from those stores, we delete those qubits, and we're going to update the counters that are internal to the repeater station object. And then I already set up for you the running the actual simulation and setting up plots. So if you run the code as is, let's try that. Nothing happens, right? So let me show you. If you run this as is, you see something like this. So the throughput is 0 and completion time 0, so there is no samples because nothing's happening in the simulation. If you implement things properly, you're going to see a linear increasing line here, something like this, and some histogram for the probability distribution of completion times in the right plot. So I'm going to give you time now to try to fill in those missing parts, and to chat. Feel free to call me there if you have any questions. I just want you to play with it. That's all I want. just as a poll, how many people have implemented it already? Okay, I'll give you some more time. I'm gonna try again. How many solved it? Raise your hands. Okay, it's okay. We'll have +2 from before. Okay. Do you want more time, or would you rather look at the solution together? More time? Okay. Okay. I could have come there. Wait, let me turn the mic off. Okay, I'm gonna poll you guys again. Raise your hand if you think you did it. Okay. For the in the interest of time, I'm going to go over how I implemented it. I have been interacting with people who have solved it in many different ways, even better than my solution. So if you're going a different route, feel free to do it. I'm just going to show you one way of doing this, okay? And if you want to check the solution, if you open the on that repository on GitHub, you open the solution branch, and you also have access to the solution files. So we use a store, right? So what the entangler does is there it is. So first, the entanglement wants to reserve the access on the link. So the way I did it is just put a placeholder inside the memory to say, okay, the memory is empty now. I have it. It's mine. You don't actually need this for this specific example. I realize it might be a little an overkill. You can get away without doing this initial step and using a resource or just only single type for the store. It's fine. Anyway, once the link has access to the every loop, every iteration, the link entangler, what it does is in this specific solution, instead of like tossing, you can do two ways, right? You can toss a coin for each attempt until the coin is below the success probability, but that time you sample k in the random variables. You sample k random variables, right? Instead, what you can do, you can just sample one geometric random variable that basically counts samples. Like it's exactly this. It's the geometric random variable is defined as the number of attempts it takes to get the first success. So in one simple sample, in one sample, you get exactly what you need. So we sample that variable, then we wait for that number of attempts. So we do the timeout. So once we have the time, once we are after the timeout, we want to put entanglement inside the memory. So we get. If we put, because at the beginning we put the empty placeholder, right? So we take that back, then we're using the get, and then we put a link entanglement inside the memory to mark the fact that that memory is now entangled. So that's all the link controller, the entangler does. The swapper, the repeater, the key thing is that the repeater has to wait on both left and right links. So what it does, it will yield get left and get right on the repeater station. These are just two functions that I defined that basically call get on the left store and on the right store of the repeater station. So you call get on both, and you yield on that with an AND operator. You want to be able to get from both. And it's important to call this together because then you can only get them you either get them both or you don't get any of those. And then you wait for some timeout if you want to implement some swap time. And then nothing, you just update the internal counters for the repeater station. So that's basically it. Now, if you run this, hopefully everything should work. You see that over time we are delivering bell pairs. And you see an empirical PDF here for the inter-arrival times of end-to-end bell pairs. Now, if I increase, so has anyone any clue of what this PDF looks like? If I increase the number of samples, what will it converge to? This is just, no, it's not discrete event simulation, it's more like probability theory, but sorry. The geometric distribution is for one of the two links, right? So it's not exactly geometric, because the geometric is just a discretized version of the exponential distribution. So the geometric, it looks like something like from a maximum, it only decreases with time, right? Whereas this, if you look at that, increasing the sample size, you will get something that starts low, then goes to a high, and then goes back to low. It's not, it will, if you have, yeah, it's not a Gaussian yet. Sorry? I'm not sure if it has, no, I don't think it's supposed to. I don't know, I don't think it has a name specifically. But it's going to be the maximum of 2 exponentials / geometric. I don't know if that has a specific name. I don't think so. But if you take the maximum of 2 geometric / exponential probability distribution, you get something that looks like that. That's all. That's all. But why it's the maximum? Because you have to wait for both, right? Then both start at the same time. So whatever takes longer. So it's a little worse. It's a little longer on average than a single geometric. Okay, so material-wise, as far as I'm concerned, we are good. We're done. If you feel we can go to lunch. However, if you want, we can also take a look at this. So a generalization of the repeater example that's pretty straightforward. It's okay, but what if instead of having just one repeater, we have a whole chain, right? I said before, we can iterate that. So if you want to play with it, now instead of only 3 nodes, you have, I set it up so that you have a power of 2 number of links. So say 5 nodes. And your goal, so basically you're going to have 1, 2, 3 repeaters, 2 end nodes. Your goal is to create entanglement between the end nodes. Okay? And the way you're going to do it, this is only one way of doing it. It's not, you don't have to do it. It's just what I chose for this simulation. Again, we're going to have 1 entangler, and that's going to be the same roughly. You're going to have 1 entangler per link. But then you have to do multiple swaps. Every one of these repeaters have to do one of those Bell state measurements. So the way you do it is, first, these 2 guys swap. So these 2 guys will do the same that this guy was doing. So as soon as there is 1 Bell pair here and 1 Bell pair here, they will swap. So these 2 swap first. And basically, you first create these 2 longer branches. 1 and 2. With some success probability, because each of one of these BSNs are probabilistic. And only then, only when these 2 branches are ready, the middle guy can do the swap itself. So only then, and once this guy does the swap, the end-to-end Bell pair is ready. So this is one way of iterating this. Now I set up a similar exercise with as the single repeater. It has some of the additional stuff you have to track, because at this point you have also to track not only if there's an entanglement in memory, but you also have to know towards which other node in the network that memory is entangled with, because you need to know that, because that's when you know that it's your turn to swap. That's the main difference. So there's going to be some additional resources, some additional metadata that we have to track. You're welcome to play with it and take a look and try to fill the code spaces there too. You're also welcome to go to lunch. The main point of this is that it's going to be painful. It's going to be clumsy, because there's a lot of things to track. It's very prone to mistakes. And this should be a good example of why you need a tool like QuantumSavory, which is what we're going to do in the afternoon session, that will do this same thing, you can set it up in 3 lines of code. That's all. That was my point. Yeah, so feel free to, because it's still pedagogical, but yeah, take a look. We can go to lunch. I'll be here for questions. Up to you.